Hello, my dear students. Welcome to IMS GATE Academy. Myself, Prateek Mishra, and I hope that your GATE preparation is doing good, right? You have given almost 8 months of your time for preparing for this GATE examination. Again, I'll repeat this. It is an aptitude test in engineering. So, my dear students, in these 8 months, and I hope this, you have developed your technical aptitude well. You have prepared your subject well, and you have revised all your concepts properly in regular interval of time. We at IMS GATE Academy came up with different series to help you revise all the concepts that you have read for past 8 months. We started with SMART method, then we again continued the same with the GATE score booster session. In the GATE score booster session, the primary concept is to make you revise the entire subject using numericals. Up just before GATE examination, we want to revise all the formulas that are there for the subjects. So today we will going to see the important formulas of structural analysis. So welcome to the quick revision session of the structural analysis. As I have told you, structural analysis has a weightage of 8 to 10 marks in your GATE examination. The level of question is very easy. In fact, if you compare the level of question of structural analysis that are asked in GATE examination, the level of question is comparatively easy than the questions which are asked in engineering service examinations also. So, from GATE point of view, structural analysis subject is one of the key scoring areas if you exactly know how to apply a particular concept or how to apply a formula for a particular structure. As the name says, structural analysis comprises of degree of indeterminacy, then we have truss analysis, then we have force method and displacement method for analyzing the structure, then we have influence line diagrams and arches and cables and matrix method. This is the total weightage of structural analysis. When I talk about the weightage of structural analysis in your GATE exam, it has a weightage of 8 to 10 marks, right? Sometimes even it is less than 4 marks and sometimes it is around 10 marks, but not more than 10 marks. So you can consider structural analysis as a subject of intermediate weightage. Questions are very easy. If you understand the diagram properly, you can very easily solve a particular structure, right? Now, beginning with this quick revision session, I would like to ask you one simple question. Why do we learn this subject? Why it is important to learn structural analysis in civil engineering? For we as a civil engineers, we need to design different type of structures. In order to design these structures, we need to analyze the structure depending upon which type of loading condition is there, right? So for different loading conditions, we usually see different types of deformations happening to the structure, okay? So when I talk about structural analysis, it simply means calculating the unknown forces that are there over the structure due to the externally applied load. In structural analysis, we calculate the unknown deformations that are happening because of this externally applied load. We calculate the unknown rotations that are happening due to this externally applied load, right? So whenever we apply any load over the structure, first of all, there will be some reactions developed inside the structure. Second is some unknown deformations will happen. It can be a linear deformation or it can be a rotational deformation. So the technique used to calculate these unknown forces, unknown deformations are exactly discussed in our structural analysis, okay? Moving on with this, when we talk about structural analysis, we need to study about different type of structures. So on a broad scale, structures are broadly of 3 types. First type of structure is known as the skeletal structure, where only one dimension is predominating. We know that for any object, there are 3 dimensions. An object can have a length, it can have a width, and it has a height. Out of these 3 dimensions, if one dimension is predominating, that is the length is more compared to height and the width, then that type of structure is known as the skeletal structure. The primary example of skeletal structures are the beams and columns that we see in our houses. When we see a column, for a column, the height of the column is predominating. The height of the column is way more than its length and width. Hence, it is classified as a skeletal structure. When we see a beam structure, this beam has a huge length compared to its depth and width. Again, its one dimension is predominating, hence it is classified as a skeletal structure. Next is your surface structure. For surface structure, two dimensions will be predominating. And when I talk about two dimensions to be predominating, the primary example is the slab casted at your roofs, right? So whenever any slab is casted for your roof, for that slab, the length and width are predominating compared to the depth of the slab. As you can see here in the diagram, the length of the slab, this length and the width of the slab is predominating as compared to the height of the slab, right? So out of three dimensions, if two dimensions are predominating, it is classified as a surface structure, okay? Next comes your solid or massive structure. Solid and massive structure are those type of structures for which all the three dimensions are predominating. It may be the length, it may be the height, or it may be the width of the structure. If all the three dimensions are predominating, then that type of structure is known as the solid structure, right? The primary example of the solid structure is the dam casted. It can be an earthen dam or it can be constructed dam, right? So for the dam casted, the length of the dam, the width of the dam and the height of the dam, all the three dimensions are predominating for this structure, hence it is classified as solid structure. When we talk about structural analysis, we will be focusing only on one type of structure, that is our skeletal structure. We only talk about the calculation of unknown deformations for our skeletal structures only. We need to analyze only skeletal structures for structural analysis. Moving on with this. So these are the different type of structures that we have. Now, these skeletal structures are further of two types depending upon the type of joint by which they are connected. If a skeletal structure, that is a beam or a column, if a beam or a column is connected by a pin, it is known as a pin jointed structure. If it is connected by a rigid joint, that is either they are welded or they are casted in the same manner in which they don't have a relative movement between each other, right? They move as a single unit, then this type of structure is known as the rigid jointed structure. For a pin jointed structure, we can have the relative motion between the two members that are connected by the use of pin. Okay, so for a skeletal structure, it is of two types. A skeletal structure can be a pin jointed structure or it can be a rigid jointed structure. As I have already told you, for pin jointed structure, there will be a relative motion. There will be a relative motion or movement between the structures or between the members which are connected using the pin. For a rigid jointed structure, there will be no relative motion. There will be no relative motion. There will be no relative motion between the members which are connected using a rigid joint. The primary example of a rigid joint is either it can be a weld or it can be a uniform cast, right? For a rigid joint, it can be a weld or it can be a uniform cast. That is, when columns and beams are casted simultaneously, they form a rigid jointed structure. They move as a single unit, right? All the moments transfer takes place through this rigid jointed structure, okay? Now, depending upon either we are having a 2D figure or a 3D figure, these rigid jointed structure can be rigid jointed plane frame or a truss or rigid jointed space frame for a truss. For rigid jointed plane frame for a truss, we are talking about 2D structures that is existing in single plane, right? If this structure is in 3D, then it is known as the space frame. The primary example of a plane frame is when you walk over any bridge, right, which is an old bridge or you can see it as a steel bridge, right? the either side of it you see a truss. Okay, either side of it you see a truss. If you consider only one side of a truss, this one side of a truss is nothing but the plane frame or a pin jointed plane frame, right? When you consider the entire structure, that is truss on the either side, then the truss on the top, then truss on the bottom above the slab, then this entire structure of the truss is known as the pin jointed space frame. Hopefully this is clear to you. Just 1 minute. Next is, similarly, if this rigid jointed structure in 2D, it is known as rigid jointed plane frame. This is for 2D. And if we talk about a 3D structure, it is known as a rigid jointed space frame. This is for 3D, rigid jointed space frame, right? So these are the different type of skeletal structures depending upon the type of joint they are having. Either they are pin jointed or they can be rigid jointed structure. Moving on with this. Next topic of discussion is different type of force system and the equilibrium equations that are there for a system. In order to analyze any structure, first of all we need to find out which type of force system is there. Depending upon the type of force system, we will decide how many equilibrium equations are applicable to it. Okay. So we have these 4 types of force system and equilibrium equations. First we have the coplanar plus concurrent force system. You can understand this for a coplanar concurrent force system. Let me draw this. For a coplanar concurrent force system, for suppose this is the plane that I am considering, the plane of my board. Okay. If I am considering the plane of my board, and if I have this type of force system which is meeting at one point, and they are all lying in the same plane. This is the force system I have. This is my force F1, then F2, then F3, then F4. This is the different type of forces that are acting and they are all meeting at a point. Say this point is O. All these forces are lying in one plane. Also, all these forces are concurrent, that is they are meeting at a point. For this type of force system, we have only 2 equilibrium equations. For this type of force system, we have 2 equilibrium equations, that is summation of horizontal forces 0 and second is summation of vertical forces 0. So if you have a coplanar concurrent force system, the number of equilibrium equations are 2, that is summation of horizontal forces 0 and the summation of vertical forces 0. So this is our first type of force system. The next type of force system is coplanar and non-concurrent force system. When we talk about this type of force system, I'll just quickly give you an example. If you have a beam like this, right? If you have a beam like this, for a beam like this beam is a 2D structure, right? This beam that we consider is a 2D structure. It is a simply supported beam. For this beam, if any external loading is there, right? If any external general loading is there, corresponding to this load, you have support reactions like this. These are the support reactions you have. Say this is my A, this is my B. So I have one reaction RA and I have a reaction RB, right? Then I have the horizontal reaction HA. As you can see, all these forces are lying in a single plane, but these forces are not meeting at one particular point. So this type of force system is known as coplanar non-concurrent force system. Okay. For this type of force system, we basically have 3 equilibrium equations. First is summation of vertical forces to be 0. Second is summation of horizontal forces to be 0. And third one is movement about Z is equals to 0. That is the transverse axis, movement about the transverse axis to be 0. So these are the 3 equilibrium equations that we have for a coplanar non-concurrent force system. Okay. So for a coplanar non-concurrent force system, we have three types of equilibrium equations. Moving on with this. So for a coplanar non-concurrent force system, the number of equilibrium equations are 3. Next is for a non-coplanar concurrent force system, the number of equilibrium equations are 3. Let us see the non-coplanar concurrent force system. If you have seen this camera stand or the tripod stand or the total stations, right? So you have this camera fixed or tripod fixed like this, right? And below this, you have this camera tripod and you have the stand like this. You have stand like this, right? You have stand like this. So all these these legs are lying in the different plane. They are not in one plane. You have two legs in the front and one leg at behind it. Okay. So for this type of force system, they are non-coplanar. Say this is F1, this is F2, and this is F3. F1, F2, F3 are non-coplanar. F1, F2, F3, F1, F2 and F3 are not lying in a same plane, are not lying in same plane, So for this type of force system, we have three equilibrium equations. First is summation of horizontal forces to be 0, Fx 0. Then we have summation of Fy to be 0. And then we have summation of Fz to be 0. So these are the three equilibrium equations that we have for a non-coplanar concurrent force system. Three equilibrium equations are there, right? Moving on with this. Last one is the non-coplanar non-concurrent force system. So just imagine any beam or any column, right, which is present in the 3D. So let me draw quickly a beam or a column in 3D. So a beam will look like this in 3D. A beam will look like this in 3D, right? Here it is supported. This is support of the beam. Here it is supported like this, right? On the other hand, it is also supported like this. This is the support of the beam. If any load is acting like this is the load acting in the vertical direction like this. Then you have any load in the transverse direction, right? This is the load acting in transverse direction. You have another load acting like this in the vertical direction and you have another load acting like this, right? All these forces are lying in three different planes. This force is in the vertical plane, this force in this side, this again it is in vertical plane, but this force is in transverse plane, right? So this is just an example. Along with that, you have support reactions like this. So all this comprises of a non-coplanar, non-concurrent force system. For this type of force system, we have three equilibrium equations. Six equilibrium equations. First is summation of horizontal Fx0. Then we have summation of forces along y-axis to be 0. Then we have summation of forces along z-axis to be 0. Then we have summation of moments about x to be 0, that is longitudinal axis. Then summation of moment about y to be 0. Then we have summation of moment about z to be 0. So these are the six equilibrium equations for a non-coplanar, non-concurrent force system. So these are the six equilibrium equations that are there for a non-coplanar, non-concurrent force system. So whenever we talk about the non-coplanar, non-concurrent force system, the total number of equilibrium equations are 6, right? So first of all, after seeing any structure, we need to decide which type of structure it is this, right? Either it has a coplanar concurrent force system, it has a coplanar non-concurrent force system. Third is non-coplanar concurrent force system, and fourth one is non-coplanar, non-concurrent force system. I would like to add one more detail, right? When we have seen these different type of structures, right, when we talk about this type of structure, when we talk about this coplanar concurrent force system, it is unstable if any moment is applied about this point O. If any moment is applied about this point O, there is no possibility by any of these forces to produce any resisting moment against this externally applied load, right? So if any force system is meeting at a point and you apply a moment about that point, then there are no chances of development of any resisting moment about this point against this externally applied moment. One more thing, same happens when you analyze this, right? When you analyze this non-coplanar concurrent force system, okay? Here also all the forces are meeting at one point. So if you apply any moment, about this point O, again there are no forces which can produce the resisting moment against this externally applied moment about this point of concurrency. So whenever force system is concurrent and if you apply any moment about that concurrent point, there will be no chances of the development of resisting moment about or against that externally applied moment, okay? So all these concurrent force system are unstable whenever any moment is external moment is applied about the point of concurrency. Is this okay? Hopefully this is clear to you. Moving on with this. So these are the different type of force system. Next, so let me just move to the next topic quickly. So these are the different type of force system. Now first of all, if we need to analyze the structure, we need to count the number of unknowns that we need to calculate, okay? These unknowns can be reactions, these unknowns can be deformations. Now how to calculate these unknown forces or unknown deformations? For that, we have a concept of determinacy, right? When we say any structure is determinate, we mean that all the unknown forces present in the structure can be calculated using equilibrium equations. When such condition happens, in that case only, we say a structure is determinate. So if all the unknown forces are determined using the equilibrium equations alone, then that structure is known as the determinate structure, okay? When some additional equations are required in order to have these unknown reaction forces, in order to calculate these unknown reaction forces, then in that case, that structure is known as the indeterminate structure. So whenever unknown reactions are determined using both equilibrium equations and additional equations that are known as the compatibility equations. If additional compatibility equations are required apart from the equilibrium equations, then that structure is known as indeterminate structure, okay? Now talking about the indeterminacy, as we have cleared that if the number of equilibrium equations are sufficient enough to calculate the unknown forces, then that structure is determinate. So here comes a concept of degree of static indeterminacy. Degree of static indeterminacy tells us about the number of extra equations required to analyze the structure. And when we talk about extra equations, we are talking about the compatibility equations, right? So the number of extra equations required to analyze the structure apart from the equilibrium equations are termed as degree of static indeterminacy, okay? So the degree of static indeterminacy ds is equals to total number of unknowns minus the equilibrium equations, okay? So this ds is equal to degree of static indeterminacy ds is equals to degree of external indeterminacy plus degree of internal indeterminacy. Please understand this. When we talk about degree of static indeterminacy, it comprises of degree of external indeterminacy. When we talk about degree of external indeterminacy, DSE, when we talk about degree of external indeterminacy, DSE, we are talking about the unknown reaction forces. Unknown we are talking about the unknown reactions, right? And these unknown reactions are usually the support reactions. So, degree of external indeterminacy deals with the unknown support reactions. Okay. On the other hand, degree of internal indeterminacy, DI, deals with the unknown member forces. Deals with the unknown member forces. Deals with the unknown member forces, right? So, degree of external indeterminacy tells us about how many extra equations are required to determine the unknown reactions, and degree of internal indeterminacy tells us about how many extra equations are required to determine the unknown member forces. Okay. So, this is about the degree of static indeterminacy. Now, so degree of static indeterminacy, DS, is equals to degree of external indeterminacy plus degree of internal indeterminacy. Now, depending upon the type of frame or the type of structure we are analyzing, there are different formulas for calculating the degree of external or internal indeterminacy. Now, we will going to see one by one. Good evening, Jagdish. A very good evening. Now, we will going to see one by one how to have these degree of static indeterminacy for different type of structures. Okay. So, first we will start with pin jointed plane frame. So, for degree of static indeterminacy for a pin jointed plane frame, so you can just imagine a plane in which a pin jointed structure is there, right? In a single plane, pin jointed structure is known as the pin jointed plane frame. So, pin jointed plane frame is the coplanar and non-concurrent force system. For a coplanar non-concurrent force system, the number of equilibrium equations are 3. We have 3 equilibrium equations in order to determine the degree of static indeterminacy, or in order to determine or in order to analyze this structure. So, degree of static indeterminacy is equals to degree of external indeterminacy plus degree of internal indeterminacy. Degree of external indeterminacy is equals to total number of unknowns minus equilibrium equations, that is R minus 3. So, ds is equals to R minus 3. Now, degree of internal indeterminacy is equals to m minus 2j plus 3. So, this is the degree of internal indeterminacy. You can directly calculate degree of internal indeterminacy using this relation. So, finally, when we add DSE and DSI, the total degree of static indeterminacy for a pin jointed plane frame comes out to be m minus 2j plus r. In the examination, you need to ensure which type of indeterminacy you need to calculate. Okay. There can be a question where you are asked only to calculate degree of external indeterminacy or only degree of internal indeterminacy. Or most general question is finding the total degree of static indeterminacy. So, please keep a check which type of question is there, right? When we talk about GATE preparation, my dear students, so you have given almost everything for past 8 months for appearing in this GATE examination. This is the time where have to be extra cautious about your concepts, right? Don't overstress yourself that how your result will come. Your process was good, you did enough hard work, and that is the sufficient thing that you can do from your side, right? You need not to worry about the results. In these last days, what happens is we try to read everything that we had in the past. Okay, don't do that. Go easy on yourself. You have read enough, you are prepared enough. The only thing is you need to believe that you have understood the concept. Still, there will be questions in which you may find it difficult to have the solution. So, don't worry about it. It is just a process. It is a continuous learning process. And still, if you have these questions which you find difficult to solve, just try to analyze those problems that exactly in applying the concept is there a problem, or in understanding the question is there a problem. The problem can be either understanding about the question, or it can be application of the concepts that you read. Okay, so try to analyze that which type of problem you have and just resolve it quickly, right? And if it is not getting resolved, let it be. Relax. Don't just freak out that you are unable to solve the question. Okay, chalo. Moving on with this. So, degree of static indeterminacy for a pin jointed plane frame, which is a coplanar non-concurrent force system having 3 number of equilibrium equations in order to analyze the structure. So, degree of static indeterminacy is equals to degree of external indeterminacy plus internal indeterminacy. Degree of external indeterminacy is r minus 3, and degree of static external indeterminacy is r minus 3, and degree of internal indeterminacy is m minus 2j plus 3, where m is the number of members, and j is the number of joints. So, this is how you can calculate the degree of static indeterminacy for a pin jointed plane frame. Next, for a pin jointed space frame is a non-coplanar non-concurrent force system. So, for a non-coplanar non-concurrent force system, you have 6 equilibrium equations in order to analyze these structures, right? So, this degree of static indeterminacy for a pin jointed space frame comes out to be ds is equals to dse plus dsi. DSE is again the total number of unknowns, that is R, right? Total number of unknowns is R, and total number of equilibrium equations, that is 6. So, the degree of external indeterminacy for a pin jointed space frame comes out to be R minus 6. Again, degree of internal indeterminacy is m minus 3j plus 6, right? It is m minus 3j plus 6. It is m minus 3j plus 6. It is m minus 3j plus 6. This is the degree of internal indeterminacy. Your total indeterminacy is just by adding degree of external indeterminacy and degree of internal indeterminacy, that is ds is equals to m minus 3j plus r. This is the total degree of indeterminacy that you have for a pin jointed space frame. Next, now we are talking about the rigid jointed plane frames. As I have already told you, for a rigid jointed plane frames, there is no relative motion between the members that are connected at a joint. So, for a rigid jointed plane frames, first one is your beams. First example is your beams. We see these beams which are rigidly fixed, right? There is no relative motion between the beams and the columns, or the beams and the supports that we see, right? So, for these beams, your degree of static indeterminacy is dse plus dsi minus number of force releases. These force releases are due to internal hinges, or it can be due to links, right? So, when we talk about any internal hinge, internal hinge gives us m minus 1 extra equations, or m dash minus 1 extra equations, m minus 1 extra equations to solve a particular structure. Okay, and what is this m? M dash is this m dash minus 1. M dash is the number of members which are connected at the internal hinge, right? If this is your internal hinge and all these members are connected, if this is your internal hinge, and all these members are connected to this internal hinge, right? So, these number of members which are connected at the internal hinge is your m dash, right? So, this internal hinge will going to give you m dash minus 1 extra equations to analyze the structure. So, we just delete or subtract these force releases, right? We just subtract these force releases. So DSE, degree of static or external indeterminacy, DSE is equals to total number of unknown reactions minus the equilibrium equations, that is R minus S, where S is the number of equilibrium equations and R is the number of unknown reactions, right? If we consider only vertical loading for a beam, for a vertical loading for a beam, there is only two equilibrium equations, that is summation of vertical loads is equals to 0 and also the summation of moment about the transverse axis is 0. If we only consider the vertical loading, we do not consider anything on the horizontal plane. So for this type of loading, summation of vertical forces is 0 and the summation of moment about point Z is 0. That is the transverse axis. Okay. If you consider the general loading, where both the vertical and the horizontal reactions will be there, in that case, your number of equilibrium equations comes out to be 3. Here S is equals to 3, right? So you need to check which type of loading is given to you. For a vertical loading condition in a beam, DSE is equals to total number of unknown reactions minus equilibrium equation, that is S. For vertical loading case, S is 2 and for general loading, S is 3, right? If we know, just 1 minute. Okay. If we know the external reactions, right? If we know the external reactions, it doesn't matter whether a beam is a determinate beam or it is an indeterminate beam, right? If you anyhow calculate the external reactions, then it is very easy to calculate the shear force and bending moment at any section in the internal structure of the beam, right? If you have these support reactions, if you know these support reactions, then you can easily calculate the value of shear force and bending moment at any section present in the beam. Okay. So for that condition or for that reason, degree of internal indeterminacy for a beam comes out to be 0. Because if you know the support reactions, you can calculate the value of shear force and bending moment at any section over the beam. Okay. So for beam, degree of internal indeterminacy is 0. Please keep a check on this. So for beam, it is very easy to calculate the degree of static indeterminacy. We will be only focusing on calculating the total number of unknown reactions minus the equilibrium equations minus the force releases. Okay. So this is the case. So force releases for hybrid joint, as I have already told you, for internal hinge, it is m dash minus 1, where m dash are the number of members joined at the internal hinge. For a shear hinge, it is 1. For internal link, it is 2, and for internal roller, it is again 1, right? So all these are the force releases that we have, and these force releases are the total number of extra equations that we get once we have these joints, right? So for a hybrid joint, these are the force releases. Next. Second is talking about frames, right? These are the rigid jointed plane frames that we are talking about, rigid jointed plane frames. In order to calculate the degree of static indeterminacy, we have 3 different methods. First method is your degree of static indeterminacy is equals to DSE plus DSI minus force releases. Again, ds is equals to total number of unknowns minus equilibrium equations, where ds is equals to m plus r minus 3j, where dse is equals to r minus 3, because 3 number of equilibrium equations are there and r is the total number of unknown forces. Next is your degree of internal indeterminacy is equals to 3m minus 3j plus 3. So this is your degree of internal indeterminacy, right? When you add these two, you will get total degree of static indeterminacy ds for a rigid jointed plane frame. It is equal to ds is equals to 3m plus r minus 3j. Now this is totally the formula based thing, right? If you go by this method, I have 2 quick methods in order to get the degree of static indeterminacy for a rigid jointed plane frame. Okay. So my method number 2 says that You can calculate degree of external indeterminacy simply as r minus 3. Now for calculating this DSI, I have one method which is DSI is equals to 3C. Now what is this C? Let us see. Let us see what is this C. Okay, moving on with the structure. So this is my structure like this. This is the structure. This is just an example of a structure. So this is my structure. This is my structure like this. So in order to calculate the degree of static indeterminacy for such type of structure, it is very easy. Now how to do this? Your degree of external indeterminacy is simple. DSE is equals to r minus 3, right? So this is for a rigid jointed plane frame. Okay. Now talking about degree of internal indeterminacy DSI, this is equal to 3C. Now what is this C? C is simply the number of closed loops that are present. The total number of closed loops that are present is the total value of this C. So here C is 4, here C is 4. So your DSI is 3 into 4, that is 12. Your DSI is 3 into 4, that is 12. This is easy. I guess this is easy. Right. So this easily you can calculate the degree of internal indeterminacy, where C is simply the total number of closed loops. C is the number of closed loops. C is the total number of closed loop, right? So this is your second method for calculating the degree of internal indeterminacy. Now next is third method is a slightly tricky, and I do not suggest my students to go with this method because usually it creates some confusion, right? So this method can again still be used, and how to do this? So method number 3 is ds is equals to dse plus dsi minus force releases. So this ds is equals to 3c dash minus n minus force releases. This gives you the direct formula for calculating the degree of static indeterminacy. Now what is this c dash? Please see. So if I have a structure like this, right? If I have a structure like this, let me take a roller support. I need to calculate the degree of static indeterminacy for this structure. So what I will do is, I'll just make a cut in such a way that every portion is a free cantilever. Every portion is a free cantilever. So C dash is number of cuts required. C dash is number of cuts required to make cantilever structures. C dash is the number of cuts required to make the cantilever structures, right? Now what is this N? Right, now observe this very carefully. When you look into this first structure, right, this is a cantilever having fixed support. So this is a kind of stable structure. If you look at like this, this is a kind of stable structure because this fixed support will going to hold this structure, right? So this is a fixed or a stable structure. When you look into this middle portion is something like this. This middle portion is something like this. This middle portion is something like this, right? Now, when you see this middle portion, due to this hinge, this structure is unstable, right? In order to restrain this structure, I need to apply one moment, I need to apply one restraining moment in order to keep this structure in stable position. So, the number of reactions, external reactions that are required to keep this structure in stable position is the value of n, right? I'll see the third. When you look to the third variety, so for the third variety, you have this roller support, and for this roller support, if you see to this cantilever that is formed, this roller support due to this hinge can move the structure, and also it can move in this direction also where the roller support is attached to the surface. So, in order to restrain this, I need to apply one reaction and one moment in order to keep this structure in stable position. So, N is the number of reactions that you need to apply from your side in order to keep this structure in stable position. So, N is, for this question, your N is 1 for this support and 2 for this support, right? So, the total value of N is 3. C dash is the number of cuts required to open the structure and to make a cantilever. So, here C dash is 2. So, accordingly, using the relation, you can easily calculate the value of your degree of static indeterminacy, that is ds is equals to 3c dash minus n minus number of force releases, right? So, n is the number of restraints added to make the joints rigid. C dash is the number of cuts required to make determinate cantilever structures. Is this okay? So, hopefully, how to calculate this is clear to you for degree of static indeterminacy for a rigid jointed plane frame. Okay. You have 3 methods for doing that. You can opt for any method, and I'll suggest you go with this method. This is one of the easiest method for calculating the degree of static indeterminacy for a rigid jointed plane frame. Okay, moving on with this. Next we have rigid jointed space frame, right? We have a rigid jointed space frame. This is space frame, not plane frame. This is rigid jointed space frame. This is rigid jointed space frame. A easy example of rigid jointed space frame is when you consider these steel structures, right? When you consider these warehouses, the initial construction of these warehouses or godowns, it is usually casted by these steel or any material of mild steel in the form of columns and beams. The initial skeletal structure of these warehouses is an example of rigid jointed space frame. Okay. Again, for rigid jointed space frame, we have 3 methods for calculating the degree of static indeterminacy. First is by using the formulas. So, ds is equals to dse minus dsi minus force releases. Your ds is equals to total number of unknowns minus the equilibrium equations. ds can be calculated as 6m plus r minus 6j. This is the degree of static indeterminacy for a rigid jointed space frame. Your degree of static indeterminacy or external indeterminacy dse is equals to r minus 6 and dsi is equals to 6m minus 3j plus 6. So, this is how you can calculate the degree of static indeterminacy for a rigid jointed space frame. Now, talking about method number 2, here also ds is equals to dse plus dsi minus force releases. Your ds is equals to r minus 6, that is your external indeterminacy, and 6c, where again c is the total number of loops present in the structure, the number of closed loops that are present in the structure, that is c, right? So, your dsi is equals to 6c. If any force releases are there, it is again subtracted from your final value of degree of static indeterminacy. This force releases are subtracted from your, the force releases are subtracted from your external and internal indeterminacy. C is the number of closed loops. Next is your method number 3. For method number 3 also, your ds is equals to dse plus dsi minus force releases. your ds is equals to 6c dash minus n minus force releases, right? Here again, c dash is the number of cuts required to make the structure a determinate cantilever. And when we are talking about rigid jointed space frame, we need to analyze this structure in 3D, right? So for 3D, the number of cuts which are required to make this structure as a free cantilever is the value of c dash, and n is the number of restraints added to make the joints rigid, right? So these number of restraints are only added when your support condition is either hinge support or a roller support. We need not to add any restraining moments or any restraining forces when we talk about fixed support, okay? So hopefully this is clear to you. Okay, moving on with this. Next is the degree of kinematic indeterminacy. First, we have talked about calculating the total number of unknown reactions. And extra number of equations which are required to calculate the number of unknown reactions are calculated using degree of static indeterminacy. When we talk about the deformations, the total number of unknown deformations that can happen in the structure, that can be determined using degree of kinematic indeterminacy. So, the degree of kinematic indeterminacy is the degree of freedom for a structure. And when we talk about the degree of freedom, we are talking about the possibility of movement. It can be a transitional movement, it can be a rotational movement. The possibility of any type of movement for a structure is termed as the degree of freedom for that particular structure, right? So, this degree of freedom or the degree of movement totally depends upon the type of support condition, okay? When I talk about a fixed support, for a fixed support, there is no possibility of movement. For a fixed support, there is no possibility of movement in any direction. When I talk about a fixed support, I'll just draw this. For this fixed support, there can be no horizontal deformation, there can be no delta x, there can be no delta y, right? And there can be no rotational theta xy, right? There is no possibility of all these movements for a fixed support. Hence, the degree of freedom for a fixed support is 0. Next, we talk about the hinge support. For a hinge support drawn like this, this hinge support cannot move in the x and y direction. It cannot have any transitional movement in x and y direction. But for this hinge support, this member can rotate about the hinge. So for a hinge support, the degree of freedom is 1. For a hinge support, the degree of freedom is 1. Next, we talk about the roller support. For a roller support, like this. So this is my roller support. For a roller support like this, let me draw this roller support like this. For this roller support, one, there can be a movement along the surface, right? And second one, there can be a rotation about this hinge. So for this roller support, two types of movement are possible. Hence, the degree of freedom for a roller support comes out to be 2. When I talk about guided roller support, so here is an example of guided roller support like this. So this is an example of guided roller support. For this guided roller support, there can be movement only along the surface, right? There can be movement only along the surface. This guided roller support provides the additional reaction with the moment that is applied over this member. So there is no rotational movement possible for this guided roller support. There can be only one movement that is along the surface possible for this guided roller support. Hence, the degree of freedom for a guided roller support is 1. So this is very important. You need to keep a check on the degree of freedom depending upon the different type of support. For a fixed support, it is 0. For hinge support it is 1, for roller support it is 2, and for guided roller support it is again 1. When we talk about the type of joints and the degree of freedom, for a pin jointed plane frame, the degree of freedom is 2, right? Let me just see this. For a pin jointed plane frame. So this is my pin jointed plane frame. This pin jointed plane frame can either move in this direction or it can move in the vertical direction. So the degree of freedom, for a pin jointed plane frame, and when I am talking about pin jointed plane frame, I am talking about the joint, right? I am talking about this joint, not about the members. For this pin jointed plane frame, it can move in the x direction and or in the y direction. Similarly, for a pin jointed space frame, for a pin jointed space frame, the degree of freedom comes out to be 3. Delta x, delta y and delta z. Okay. For a rigid jointed plane frame, the degree of freedom is 3. That is delta x, delta y and theta. There is a rotation about the rigid joint possible, right? And for a rigid jointed space frame, the degree of freedom is 6. That is delta x, delta y, delta z. I'll just write down all these things. So, for rigid jointed plane frame, the degree of freedom is due to delta x, delta y and theta xy, right? For a rigid jointed space frame, for a rigid jointed space frame, I have these translation movement delta x, delta y and delta z. Then I have theta xy, theta yz and theta xz. Due to all this, the total degree of freedom for rigid jointed space frame is 6 and for rigid jointed plane frame it is 3. So keep a check on the type of joint that is there. First is the type of support, second is the type of joint that is present. Okay, moving on with this. Next is your type of hinges and the degree of kinematic indeterminacy. First one is your axial shear hinge, right? Understand this very carefully. When I talk about axial shear hinge, so this is my axial shear hinge. This is my axial shear hinge. This is my axial shear hinge, right? For axial shear hinge, there is no transfer of your axial stresses to the another member. For this axial shear hinges, I have 4. One that is delta x. For this member, I have delta x2, right? Then I have one delta y for this member, right? So for an axial shear hinge, the total kinematic indeterminacy is 4 or degree of freedom is 4. And last one is your rotation, that is theta xy. For your axial shear hinge, these are the 4 different types of movement that are happening. So this is your axial shear hinge. So this is your axial shear hinge, right? Similarly, when we talk about the axial vertical hinge, so when I talk about the axial vertical hinge, it will be something like this. So this is your axial vertical hinge. for this axial vertical hinge, you can have one translation like this. This is my delta y1, this is my delta y1, this is my delta y2 for this member. Then I have theta xy, then I have theta xy, and next we have the translation movement like this, that is delta x, right? So these are the four different movements that are happening for a vertical shear hinge. So for a vertical shear hinge, for a vertical shear hinge, for a vertical shear hinge, the degree of kinematic indeterminacy is 4. That is, the degree of freedom is 4. Next one is your, I'll just, your internal hinge, right? And I have already told you, for your internal hinge like this, for your internal hinge like this, right? This internal hinge can have these varieties of movement. First one is your delta y, second one is your delta x, this is your second. Next, you can have rotation, that is theta 1, this is theta 1, and this is your theta 2 for two different members, right? So these are the four possibilities of movement when we talk about the internal hinge. About this internal hinge can go in the forward direction, it can go in the vertical direction, forward or backward direction, that is delta x, it can have a translation in delta y, or it can have the rotational movement of theta 1 and theta 2. So that is how your kinematic indeterminacy is 4 for your internal hinge, right? So just considering all these things, you can calculate the kinematic indeterminacy for a structure. So for a pin jointed plane frame, the kinematic indeterminacy is 2j minus r, where j is the number of joint and r is the number of support reactions. Okay. For a pin jointed space frame, your kinematic indeterminacy is 3j minus r. Again, j is the number of joint and r is the number of support reactions. When we talk about the rigid jointed plane frames, for a rigid jointed plane frames, if the members are extendable, then for beams, the degree of kinematic indeterminacy is 3j minus r plus extra degree of freedom due to hybrid joints, right? So we have seen the axial shear hinge, vertical shear hinge, internal hinge, all these are classified as the hybrid joints, right? So you need to add the extra degree of freedom due to these hybrid joints. So for a beam, if the members are inextendable, then the degree of kinematic indeterminacy is 3j minus r plus extra degree of freedom due to hybrid joints. Similarly, for inextendable members, right? Now the members cannot extend. Good evening, sir. Good evening, Atul, sir. If the members cannot extend, then your degree of kinematic indeterminacy is 3j minus r minus m plus extra degree of freedom due to this hybrid joint, right? M is the number of members that are present in the beam, or the number of beam spans that are there. If we consider that these members are inextendable, that is, these members cannot undergo the translation movement, right, along their axis, along their longitudinal axis, they cannot have any movement. They even cannot extend along that, right? So for that, your degree of kinematic indeterminacy is 3j minus r minus m plus extra degree of freedom due to hybrid joints. When I talk about frames, so for extendable members, the degree of kinematic indeterminacy is 3j minus r plus extra degree of freedom due to the hybrid joints. Similarly, if I talk about the inextendable member, it is 3j minus r minus m plus extra degree of freedom due to these hybrid joints. So using all these relations, you can simply calculate what is the degree of kinematic indeterminacy for a particular structure. Okay. So hopefully both the things, that is the degree of kinematic indeterminacy and the degree of static indeterminacy is clear to you. Have a break of 5 to 10 minutes and then we will resume back for analyzing the structure. Okay. Thank you. Welcome back, my dear students. So we are studying about the quick revision of structural analysis, right? How to do that revision efficiently. We have designed this entire thing, which includes all the formulas, right? We discussed all the questions, important concepts when we have gone through this gate booster sessions. You can go back to these gate booster sessions and check the important numericals that are there that can be asked in your gate examination. So you can check our gate booster sessions as well for even revising a particular concept through questions. Okay, here we will quickly going to see about the different formulas and assumptions that are there for solving different structures. So we have seen the degree of static and kinematic indeterminacy, and we are talking about in order to analyze these structures, we need to determine the total number of unknown reactions or unknown deformations. In order to determine the total number of unknown reactions, we need to check about the degree of static indeterminacy. In order to check about the total number of unknown deformations, we need to keep a check on the degree of kinematic indeterminacy. Okay. Now moving ahead, the next topic of discussion is the analyzing of structures or trusses. So next topic of discussion is analysis of trusses. For analyzing the trusses, we need to have few assumptions. First is all the members of the truss are perfectly straight. We assume this and we construct the trusses in such a way that all the members are perfectly straight. When we talk about the joints that are present over the structure, over this trusses, all the joints are pin joint, and we know that these pin joints cannot transfer moment from one member to the another member. So for trusses, we only analyze for axial stresses or axial forces. Member of a truss is only and only analyzed for axial forces. Okay, that's why we need not to consider any member of a truss to be a curved member. First assumption is all the members of a truss are a straight members. Next is individual members are connected with frictionless hinges. As I've already told you that all these members are connected by the frictionless hinges. If you talk about the connections that are present in the truss, so these are your frictionless hinges. So these are your hinges through which your truss members are connected, right? These are your hinges through which your truss members are connected. Next assumption is load is acting only at the joints. Again, there is no calculation of the bending moment. That's why we apply loads only at the joints, right? So that only axial forces comes in the member of the truss. In order to avoid development of any bending moment, all the loads are applied at the joint because these trusses are only analyzed for axial forces. Self weight of the member is neglected. And last one is members will be subjected to only axial force. There will be no bending moment and shear force present over the members, right? So these are the assumptions that we take when we analyze any structure or when we analyze any truss. First is all the members are straight, perfectly straight. All these members are connected by a pin joint or a frictionless hinge. Third one is the self weight of the member is neglected. And fourth one is all the loads are applied at the joints. No load is applied in between the member, right? So if I consider a simple truss like this, if I consider a simple truss like this, for this truss, all the members are perfectly straight. Let me just quickly draw it. So for this truss that is drawn, for this truss, all the members are perfectly straight. All these are joints by pin joints. All these are pin joints. The loads are only applied at the joints. The external load are only applied at the joints. There will be no in-between load like this. This type of load will not be there because this type of load will going to produce the bending moment over the member. Okay. Now, this is the assumptions that we take for analyzing our trusses. In order to analyze the truss, we have three different methods. First one is the zero force members, that is using collinear theorem we can analyze. Second one is the method of joints, and third one is the method of sections. So these are the three different methods for analyzing the truss. First, we'll check on the zero force members or the collinear theorem. When two non-collinear members are meeting at a joint which does not have any external load, please take care of this, any external load and reaction, then forces in both the members will be a zero force member, right? So let me just show you what I am saying here. If suppose two members like this are meeting at one particular joint, this is one particular joint, and over this joint A, there is no external force or reaction acting. If two members are meeting at one joint and over which no external load or reaction is acting, then force in both the members will be zero. So these two are termed as the zero force member. So this is the first possibility. Second possibility of zero force member is when three members are meeting at a joint, like this, and no external force is acting over this joint. Right? And out of these three members, if two members are collinear, for this member AB and member AC are collinear, then the force in the member AD will be zero force, right? Whenever three members are meeting at a joint which does not have any external load or support reaction, then if two members are collinear, then the force in the third member will be zero force. So force in member AD will be zero force. So force in member AD will be zero. So this is my second category. Now talking about the third category, for suppose if two members are meeting at a joint, like this, so this is my joint A, this is my member AB and AC, right? If two members are meeting at a joint like this, and over this joint, one force is acting which is collinear to the one of the members, right? This force is acting and this force is collinear to one of the members. So this is the force that is acting and it is collinear to the member AB. Then in this case, force in the member AC will be zero. So if two members are meeting at a joint and the external load or the support reaction is in line with one of the members, then in that case, force in the third member is zero, right? So hopefully you have understood these three cases of zero force member. First one is when two members are meeting at a joint and the joint does not carry external load, then force in both the members is zero. Second one is when three members are meeting at a joint such that two members are collinear. This member need not to be perpendicular. It can be aligned in any of the angles, right? If two members are collinear, then force in this third member will be zero force. And third one is whenever two members are meeting at a joint and the external force or the reaction is in line with one of the member, then the force in the third member is again a zero force member. Okay. So these are the three conditions of zero force member that I have written in the form of statements. So second is when three members are meeting at a joint which does not have any external load or reaction such that two members are collinear, then the third member is a zero force member. And when two non-collinear members are meeting at a joint such that line of action of external forces or reaction, is collinear with one of the member, then the other member is a zero force member. So these are the three possibilities of zero force member. Moving on with this. Next method for analyzing a truss is known as the method of joints. Method of joint is very simple. First, you need to calculate the support reaction. So I'll just write down the step. First, calculate the support reaction. Calculate support reaction, and then consider joint in which only two unknown forces are there. In which I'll just write down this block, only two unknown forces are there. 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 Only two. Because for every joint, we have only two equations of equilibrium, that is summation of Fx0 and second one is summation of Fy0. So for every joint, we have only two equilibrium equations. Hence, we consider only those joints which have only two unknown reaction forces. Is this okay? So this is how you go joint by joint in solving a question using method of joints. So here you need to find out forces in the members, right? You need to find out forces in the members. So in order to find out the forces, what I can do is, first I'll find the support reaction. So here I have a roller support and at A, I have a hinge support like this. So this is your HD, this is your HD and this is your HA, and this is my VA. This is my VA, right? First of all, I'll take the summation of vertical forces 0, summation of vertical forces 0. So from here I have this VA is equals to W, which is acting in the downward direction. So this VA is W, right? Next is your summation of moment about point A to be 0, about point A to be 0. So first moment I'll be having due to this W load. So this is W into L in clockwise direction. So this is WL in clockwise direction. And there will be another moment due to this HD, and this is also we have assumed in this direction. Hence this is also clockwise. So this comes out to be HD into L, comes out to be 0. So from here I have the value of HD as minus W, and it simply means that whatever direction we have assumed for HD, we need to reverse this direction. So this HD will be acting in the opposite direction. This HD will be acting in this direction. This is my direction of HD. Okay. Now for finding this HA, I'll take summation of horizontal forces to be 0. So summation of horizontal forces to be 0. So this HA plus HD comes out to be 0. So this HA is equals to minus HD. So this HA is nothing but equal to W. This HA is equal to W, right? Because HD is minus W. So this is how we can calculate the value of HA. Okay. So this is how we have calculated the support reaction. Now moving forward with this, I can just consider this joint A, right? For this joint A, I have two member forces, that is HD and AB, right? AD and AB. For this joint A, I'll just consider this joint A. Considering joint A, consider joint A. So for this joint A, like this, right? I have one force acting like this. I have assumed this to be compressive. This is my joint A, right? This is A, this is AB, force in the member AB, and then I have force in the member AD. This is force in the member AD, right? This is also I've assumed to be compressive. These are my external reactions. This is HD, this is HA, and this is VA. This is VA. VA is also equal to W, and HA is also equal to W. When you take the summation of horizontal forces to be 0 for this joint, when you take summation Fx0 for this joint A, you will find that force in the member AB will be equal to HA, that is nothing but your W, right. So, this is your first force in the member AB. Second, force in the member AD can be taken or can be calculated by simply taking the summation of vertical forces to be 0. So, this is FAD is equals to VA, which is again equal to W. So, that is how you can proceed and calculate the member forces using joint by joint, right. You need to move from one joint to the another joint in order to calculate all the member forces for this type of truss. So, this is how you can move with method of joints. You can analyze this joint, then you can analyze this joint D, because for this joint D you have two unknown forces. First is FDC and FDB. Then you can go for this joint C. So, for this joint C, since no external forces are acting, we can directly say that force in the member CD and CB are zero force members, right. So, this becomes more easy by just compiling the zero force member with the method of joints. So, first calculate the support reaction, check for zero force member, and then try to analyze the structure by moving from every joint, one joint to the another joint. Consider only those joints where two unknown reactions are present, because for a joint only two equilibrium equations are available to us. Okay. Now, moving on with this, next method for analyzing a truss is the method of section. Okay. For a method of section, it is again a very simple technique. For method of section, the basic concept is, if the entire structure is in stable equilibrium, then even the segment of that structure will be in stable equilibrium only. Okay. These forces are developed in such a way that even if you consider a segment of a structure, that will be in stable equilibrium. Okay. So, what we do in method of section, first we calculate the support reaction, and after calculating the support reaction, for suppose in this question we need to find the force in the member AB. So, what I will do is, I will just take a section like this, cutting not more than 3 members. Cutting not more than 3 members. I will just take a section like this. Let me draw this. So, this is the section that I took, right. This is the section that I took. After calculating the support reactions, the forces can be this is F1, this is F2, and this is F3, right. So, these are the forces which are present in the member, and all these forces are assumed to be tensile. This calculation, right, these direction can be reversed while calculating the forces, that is no problem. For this support, you have one vertical reaction VA and you have one horizontal reaction H, right. So, this is your support reaction. You need to find the force in the member AB, that is force F2 you need to find, right. You have taken a section, and after taking the section, this is the force diagram or the free body diagram of the either left of the structure or right of the structure. Here I have taken the left of the structure. I have considered this part. I have considered this part of the structure. If required, you can take even the right side of the structure. That is not a problem. Only thing is, which part is convenient to you to solve, you can consider that segment of the structure, right, for solving this through method of sections. This is one of the easiest method when we talk about the complicated structures or complicated trusses. For complicated trusses, in order to find out the member force for the intermediate members, this method of sections proves to be the most efficient method, because if you go by method of joints, you need to analyze every joint to get this member force AB, and at least you need to analyze 1, 2, 3 joints in order to get this force in the member AB. But in method of sections, you have to simply take a section cutting not more than 3. members, right? And why we are saying this? Because for plane frame, we have three equilibrium equations, that is summation fx0, summation fy0, and the moment is 0, right? So moving on with this. So we have taken the left side of the structure like this. We have considered the left side of the structure like this. For this left side of the structure, first thing is you can take the summation of vertical forces to be 0 and get this F1, F2, F3, or you can have summation of horizontal forces to be 0, that is summation Fx0, and last one is you can take the summation of moment about any point to be 0, and using these three equilibrium equations, you can analyze all the unknown forces. Here the total number of unknown forces are F1, F2 and F3. These unknown forces can be calculated using three equilibrium equations. So method of sections is preferred over method of joints when we talk about analyzing any structure, right? Now moving on with this. So this is how you analyze any structure, analyze any truss, either using zero force member or using method of joints or method of sections. Now talking about the different methods that are available for analyzing the structure. So we have two types of method. First one is the force method and second one is the displacement method, right? Now which method to be choose? Every method will going to give you the unknown forces and the unknown deformations, right? So how to decide which method to be applied over any structure? So we will discuss about two things. First is the unknown reactions. When we talk about calculating the unknown reactions or just counting the total number of unknown forces that are present, right? We talk about degree of static indeterminacy. And when we talk about calculating the total number of unknown deformations or counting the number of unknown deformations, we talk about degree of kinematic indeterminacy. So just imagine if I'll give you the structure and ask you which method is applicable or which method I should use in order to analyze the structure. You will think like, sir, if unknown forces are less, we can use only that method which first calculate the unknown forces, and using these unknown forces we can calculate the unknown deformations, right? So this method is known as the force method, where you take forces as unknowns. And how you have decided to take forces as unknowns? By comparing the degree of static indeterminacy with the degree of kinematic indeterminacy. If your degree of static indeterminacy is less than degree of kinematic indeterminacy, it says that your number of unknown forces are less as compared to the unknown deformations. Okay. So whenever your degree of static indeterminacy is less than your degree of kinematic indeterminacy, you can easily say that, sir, we will going to use the force method for analyzing this structure. Next is, these force methods are also known as the compatibility or flexibility methods, right? Next is, when your number of unknown forces are more, means your unknown deformations are less. That is, your degree of kinematic indeterminacy is less than the degree of static indeterminacy. In that case, you go with the displacement methods for analyzing any structure. Displacement methods, in displacement methods, deformations are taken as unknowns, that is theta and delta, and using these deformations, first we calculate the unknown deformations, and using these deformations, we calculate the unknown reactions or the member forces that are there, right? So when displacement method is applied, only when your degree of kinematic indeterminacy is less than your degree of static indeterminacy. These methods are also known as the equilibrium methods or the stiffness methods. These are the list of your force method and your displacement method. Force method are method of consistent deformations, your strain energy theorem, your flexibility matrix method, your column analogy, and the three moment method. These methods we usually study in SOM, strength of materials, especially your three moment method and column analogy especially. And related to these two methods, right, hardly any questions are asked in GATE examination from structural analysis. There will be a majority of question there will be a majority of question there will be a majority of questions which are solved by strain energy theorem. And for using this strain energy theorem, you need to have a clear cut understanding how to calculate the strain energy for a particular structure. Okay. Along with that, you even need to have a quick hand over the standard results of strain energy. So, two things are required. First is you need to remember the direct, or what I should say, the standard results for strain energy for different loading conditions for different type of beams. And second one is you need to understand, using this strain energy, how to calculate the deformations. That can be your transitional deformations delta, or it can be your rotational deformations theta, right? So, how to do that? This strain energy theorem is one of the most important theorem when I talk about the questions in structural analysis. Moving on with this, when we talk about the displacement method, we have the slope deflection method, then we have the moment distribution method, then we have the stiffness matrix method, and last one is the Canny's rotation method, right? So, when we talk about all these methods, usually long conventional questions are framed using these methods, right? For slope deflection method, you need to write these slope deflection equations, and then you need to solve these simultaneous equations for different values of deformations. When we talk about the moment distribution method, you need to keep a check on the number of iterations that are required to solve or get the exact value of the member forces. Okay, so we will going to see this one by one. Moving on with this. So, first is, there are few assumptions for analyzing the structure, right? First assumption is we consider the structure to be homogeneous, isotropic and elastic. What we mean by homogeneous and isotropic material? If we take a material, if the properties of the material are same in all the directions at all the points within a structure, then that material is known as the homogeneous material. If the properties of a material is, if I consider a material like this, at every point of the material, if the properties of the material are fixed or constant, it may be Poisson's ratio, it may be refractive index, it may be modulus of elasticity E. So, if all these properties of the material are same at all the points within a material, then that material is known as, or that structure is known as, homogeneous and isotropic structure. We only consider the structure up to the elastic range. We do not go for the plastic analysis, right? We only go up to the elastic range. Next is, structure follows Hooke's law. As I have already told you, we consider only the proportional limit. Up till the proportional limit, we consider the structure to deform, right? So that if we remove the load, the structure will going to regain its original shape and size. So, structure follows Hooke's law. Next is, last is, it has the first order linear analysis. What is first order linear analysis? First order means that even after deformation, right, even after the deformation has happened, usually when we apply load, these deformations are very less with compared to the original length of the member, right. So, we do not consider the member to change its length. That is termed as the linear deformation. Length of the member before the load is applied and after the load is applied, we consider it to be same, keeping the check that minute deformations that are occurring, right. So, the length of the member before application of the load will be same as length of the member after application of the load. Next is your linear analysis, where the load is directly proportional to the deformations. So, this is your first order linear analysis. So, when we talk about analyzing any structure, these three assumptions we keep in mind, right. We do not load the structure beyond the elastic limit, and also we consider a material to be homogeneous, isotropic and elastic. Okay. And again, it is a first order linear analysis. Moving on with this. So, first is your strain energy principle. Understand this. What do we mean by strain energy? So strain energy is the energy stored in a structure when it is undergoing deformation, right? When you apply load over any structure, due to this external load, the material will going to deform, right? And this deformation of the material will going to store some amount of energy. That is the energy which is required to deform the structure. The energy which is required to deform the structure will be stored inside the structure in the form of strain energy, right? So that is the strain energy. Strain energy can be calculated as by calculating the area under the load displacement curve. So when we talk about gradual loading, so this is my load displacement curve. This is my load displacement curve. This is my load displacement curve for the gradual loading, right? So area under this curve, this area under this curve is this amount of strain energy that is stored. And this area is half into P into delta, where P is the gradually applied load, this P is the gradually applied load, this P is the gradually applied load, and corresponding to this gradually applied load, delta is the deformation that happened, right? So P is the gradually applied load and delta is the deformation that took place due to this P. When we talk about the impact loading, the strain energy is P into delta. So for impact loading, the graph of load displacement curve is like this. So this is the graph of load displacement curve when we talk about impact loading, right? This is your impact loading. This is your impact loading. This is P and this is delta, right? This is delta. So area under the curve will be P into delta. So for impact loading, the strain energy stored will be P into delta. That is how you can calculate the strain energy for any structure. So deformations can be caused by the axial forces, shear forces, or bending moment or twisting moment. So any kind of deformations that are caused by any of these forces will going to add up strain energy to the system, right? This strain energy for axial deformation can be calculated as half P into delta. That is nothing but half P, and delta can be written as PL by AE. On multiplying these two terms, we have the strain energy due to axial deformation as P square L upon 2AE. Last is your total strain energy due to axial deformations is sum of the strain energies for every member. This is the sum of the strain energies for all the members that are connected in a particular structure. So due to axial deformation, the strain energy which is stored is P square L upon 2AE. And if we talk about the total strain energy for a system, it is the sum of the strain energies for all the individual members. Okay, so this is how you can calculate the strain energy due to axial deformation. Next is, using the strain energy, we can also calculate the deformations. It can be your vertical deformation or it can be your rotational deformation, right? Vertical or horizontal deformation depending upon the type of load which is acting. So for a linear elastic structure, the partial derivative of the strain energy with respect to the load will give you the displacement at the point of application of the load in the direction of load applied. So if I consider a structure like this over which a vertical load is applied, so I have to just write down the strain energy of this system and I have to partially differentiate the strain energy with respect to this load W. This partial derivative of strain energy with respect to load W will going to give me the deformation that is occurred, will going to give me the deformation that is occurred, will going to give me this deformation, will going to give me this deformation delta which is occurred. So this delta B can be calculated as partial derivative of strain energy with respect to this load, right? In order to calculate the rotation due to this moment, I have to partially differentiate the strain energy with respect to this moment, So this theta B is partial derivative of strain energy with respect to this moment. So this is my rotation This is my value of rotation using Castigliano's theorem. So these are the two applications of Castigliano's theorem. For according to Castigliano's theorem, if you need to have the deformation in any direction, or if you need to have the rotation about any point, you need to calculate the total strain energy of the system, and with respect to the load that is causing that deformation, you need to partially differentiate the total strain energy, right. So here if you partially differentiate the total strain energy with respect to W, it will going to give you this deformation delta. Similarly, if you partially differentiate the total strain energy with respect to this moment, you will going to get the rotation of this point where the moment is acting, and that theta can be calculated as del U by del M. Moving on with this. So these are the standard results of the strain energy due to bending. The strain energy is U is equals to integration of mx square upon 2EI into dx, right, where mx is the moment at any section xx, right, moment at any section xx. Similarly, strain energy due to shear is U is equals to just 1 minute. So U is equals to integration of Vx square upon 2Ag into dx, right. So using this, you can calculate the strain energy due to shear force Vx acting at any section xx. Strain energy due to torsion is equals to U is equals to integration of Tx square upon 2Gj into dx. So these are the standard results for calculating the strain energy due to bending moment, due to shear force, or due to torsion, right. Once you have calculated this strain energy for the system, you can easily calculate the deformation using the Castigliano's theorem. So delta, as I have already told you, this delta is equals to del U by del W, and this del U can be written in form of moment, that is del U by del W, or del U by del W is integration of mx del mx by del W into dx upon EI. So this is the direct relation for calculating the deformation using Castigliano's theorem. Moving on with this, when we talk about calculating the member force for a truss, or sorry, when we talk about calculating the deformation for a truss or a plane frame, right, we have this unit load method, in which the first case is if external loading is present, then the deformation delta is summation of k into delta dash. This delta dash is KL upon AE. So what you have to do is, for external loading case, first you need to consider and analyze the structure due to external load. Due to external load, you need to analyze the structure, right. After that, second step what you have to do is just remove this external load and apply the unit load in the direction of deformation that is required. In the direction of deformation, that is, if you require a vertical deformation at any point, apply the vertical unit load at that point and again analyze the structure. So due to this external load, you will going to have the P values for every member, and due to this unit load, you will going to have K values for all the structures, for all the members, right. So you have to just take the summation of PKL by AE. P is the member forces due to external load, and K is the member forces due to the unit load applied in the direction of required deformation. Next, we have the temperature change case, where the delta can be calculated as summation of K into delta dash. This delta dash is the change in length due to the increase in temperature of the member, right, and this delta dash is equals to L alpha T. K is again the force in the members due to the unit load applied in the direction of deformations which is required. And last one, due to lack of fit, total deformation delta is summation of K into delta dash, which is equal to summation of K into D into Li, where this DLi is the lack of fit. DLi is positive if the length of the member is more, and DLi is negative if length of the member is less, right. So this is how you can do a question using unit load method. Have a break of 5 minutes and we will continue in 5 minutes, okay. Welcome back. We are discussing about how to analyze the structure using strain energy methods. So here are some of the standard results of the strain energy. When we talk about the strain energy stored due to point load, it can be calculated as strain energy stored due to point load. It is equal to W is equals to W square L upon 6I, and this is for a cantilever beam. If you consider a cantilever beam like this, for this cantilever beam over which point load is there, point load is applied at the free end like this, right? So then the total amount of strain energy which is stored is W square L cube upon 6Ci. For same cantilever beam, if you have this moment that is applied at this free end, so if you apply a moment at the free end, the total amount of strain energy stored will be equal to m square L upon 2ei. Just remember these standard results, right? Remember these standard results. Similarly, if there is a UDL acting over this cantilever beam like this, then the total amount of strain energy which is stored is equal to this total amount of strain energy stored due to this UDL, which is W kilonewton per meter. This is equal to your W square L to the power 5 divided by 40 EI, right? So this W is the intensity of loading, L is the length of the member, and EI is your flexural rigidity, EI, right? Next is strain energy stored due to the central point load in a simply supported beam, right? So this is equal to U is equals to W square L cube upon 196 EI. Then the strain energy stored due to UDL in the entire span, this U is equals to W square L raised to power 5 upon 240 EI. So these are some of the standard results of the strain energy which you can remember directly in order to get the deformation by using the Castigliano's theorem. Moving on with this. So next is your moment distribution method for analyzing any structure. Going into the entire moment distribution method, first of all understand this, there are few basic properties, right? And if a question is asked from a moment distribution method, there is high possibility that the questions can be asked from the basic concepts. So first one is, what do we mean by absolute stiffness of the member? So absolute stiffness of the member is the force required for causing unit deformation. Stiffness means the amount of force required to cause the unit deformation, right? So if we talk about the axial stiffness, we are talking about the axial force which will cause unit deformation in the axial direction. If we talk about the flexural stiffness, we are talking about the amount of movement required to cause unit rotation, right? So rotational stiffness of the member is the amount of movement required to cause unit rotation. So rotational stiffness of the member is m by theta, right? So when far end of the member is fixed, your K value is, your rotational stiffness comes out to be 4 EI by L. When far end of the member is hinged, the value of rotational stiffness K is equals to 3 EI by L. When far end of the member is free, the value of rotational stiffness K is equals to 0. So depending upon the end conditions, we have three different types of stiffnesses. Obviously, if you have a fixed end, then more moment will be required to go with the unit rotation. If far end is hinged, somewhat less moment is required. So for fixed end, your value of rotational stiffness comes out to be 4 EI by L, right? Then when your far end of the member is hinged, the value of rotational stiffness K is equals to 3 EI by L, and when far end of the member is free, the value of rotational stiffness comes out to be K is equals to 0. Next, what do we mean by stiffness of the joint? When we add all the stiffnesses of the members meeting at a joint, that is termed as the stiffness of the joint. Say, if more than two members are meeting at a joint, for suppose this is the joint, where more than two members are meeting at a joint, depending upon different type of different type of support condition, there will be different stiffnesses for this joint. Say this is K1, K2, K3 and K4. If I need to calculate the stiffness of the joint, so stiffness of the joint is simply the summation of stiffnesses of the members which are meeting at a joint. So if I just add up all the stiffnesses of the members which are meeting at a joint, this will going to give us the stiffness of the joint, right? Moving on with this, then we have the relative stiffness of the member. So relative stiffness of the member is the ratio of the moment of inertia and length of the member. So when your far end is fixed, your relative stiffness is I by L, and when your far end is hinged, it is 3I by 4L. So this is your relative stiffness. Moving on. Distribution factor is simply the stiffness of the member divided by the stiffness of the joint, right? You need to calculate the stiffness of the member and divide it by the total stiffness of the joint will going to give you the distribution factor. Then we have carryover moment. So when your far end is fixed, your carryover moment is m by 2. When your far end is hinged, your carryover moment is 0, and when moment is applied at the free end of the cantilever, your carryover moment is minus m. So these are the values, you need to keep a check on that. Then carryover factor can be calculated as carryover moment divided by the applied moment. So when your far end is fixed, your carryover factor is 1 by 2. When your far end is hinged, your carryover factor is 0, and when your cantilever beam, your carryover factor is minus 1. So how this carryover factor for far end fixed is 1 by 2. When your far end is fixed and you have applied the moment, then your carryover moment is m by 2 and applied moment is m. So when you divide the carryover moment m by 2 with the applied moment m, you will get the value of carryover factor as 1 by 2. So this is m by 2 divided by m. So from here carryover factor is 1 by 2. Next, for your far end is hinged, your carryover moment is 0. Hence 0 is the carryover moment divided by the applied moment m. So here the carryover factor comes out to be 0. For a cantilever beam, your carryover moment is minus m and applied moment is m. Therefore, your carryover factor is minus 1. So these are the basic properties from which the questions can be asked in the moment distribution. Moving on with this, these are some of the standard results for the fixed end moments, right? So if you have a fixed beam, over that your fixed end moment can be calculated for a vertical load like this, right? When you have a beam and you need to calculate the fixed end moment due to this central vertical point load W, it can be calculated as minus PL by 8 and PL by 8. This is your fixed end moments, right? When your load is acting eccentrically from A distance from joint A and B distance from joint B, then your fixed end moment is PB square A by L square for FAB, and FBA will be PBA square by L square. Next, if your two loads are acting which is at a distance of A alpha from both the supports, then your fixed end moment at support A is minus alpha into 1 minus alpha into PL. For support B, it is alpha into 1 minus alpha into PL. So these are the standard results for calculating the fixed end moments for different types of point loads. Next is for different types of UDL. If your UDL is acting of uniform intensity W, then your fixed end moment at end A is minus WL square upon 12, and for end B it is WL square upon 12. If you have a UDL up to the half length, right, this is your mid length of the beam. If you have the UDL up till the half length, that is L by 2, then your fixed end moment with the end which is close to this UDL is minus WL square by 192, and the end which is away from this UDL, it is plus WL square by 192. Similarly, if you have a trapezoidal loading like this and the slope of the trapezoid is at a distance of alpha from both the supports, so your fixed end moments for support A is minus W into L cube minus 2a square into L plus a cube divided by 12L. Then for support B, it is plus W into L cube minus 2a square L plus a cube divided by 12L. So these are the standard results for fixed end moments when we talk about the uniformly distributed load. Next is for a uniformly varying load, the results of fixed end moment is, if you have a uniformly varying load and W is the load intensity for the end A, so to this end A, which is close to the highest load intensity, the fixed end moment is minus W into L square divided by 20, and for the far end it is plus W L square divided by 30. For a triangular loading like this, for end A, the fixed end moment is minus 5W L square upon 196, and for end B, it is plus 5W L square upon 96, right? Next, for two triangular loadings, for end A, it is minus 17W L square upon 384, and for end B, it is plus 17W L square upon 384. Moving on with this. So these are the standard results for fixed end moments due to the rotation, right? If your end B is rotating by delta, then the fixed end moment that is generated is plus W4 EI theta by L, and for end B is 2 EI theta by L. For end A, for end B, getting a deformation of delta, then the amount of fixed end moment that is generated at end A is minus 6 EI delta by L square, and for end B it is minus 6 EI delta by L square. So these are the fixed end moments due to the rotation and due to the deformation or sinking of any structure, right? So you can do the questions of moment distribution method only by applying the properties, right? So the initial basic concepts that we have seen for moment distribution method, majority of questions are asked there itself, right? Now moving on with this, the next method for analyzing any structure is the slope deflection method. So slope deflection equation is a relationship between moment of various members meeting at a joint and their deformations, right? So if we have a beam like this, this is my joint A, this is my joint A, this is my joint B, this is my joint B, and then I have my joint C, right? So if I need to write the slope deflection equation between this span AB, right? So slope deflection equation between the span AB can be written as MFAB. First we will fix both the support and calculate the fixed end moments, plus 2 EI by L 2 into theta A. This is for MAB, right? This is for MAB. This is my MAB. This is my MAB, right? So if I talk about MAB, I need to consider 2 theta A first, then theta B minus 3 delta by L. This delta is the general case of sinking if happening, right? If sinking is not happening, then you can just avoid this. Next is MBA. If I talk about the other end, right? So this MBA can be written as fixed end moment of MFBA plus 2 EI by L plus 2 theta B. If I am writing for end B, I will consider here 2 theta B plus theta A into minus 3 delta by L. Always keep a check that in both the equations, minus 3 delta by L is along with the minus sign. And when I talk about this delta happens like this, right? This delta happens like this. We consider the sinking of support B lower to support A. We consider sinking of support B lower to support A. In this case only, this minus sign will be there and 3 delta by L is written, right? If the other case is happening, that is end A is sinking more than end B, then here you will accordingly change the sign, right? So writing down this slope deflection equation and solving this slope deflection equation for theta AB and delta, you can easily get the value of all the unknown forces or the moments that are present, okay? So this is the slope deflection equation. Usually large questions are formed using slope deflection equations. Some of the standard results for slope and deflection for simple beam is, if you have a cantilever beam, for a cantilever beam, If you apply a moment m at free end, then slope developed at B, this beam will going to deflect like this. This beam will going to deflect like this. So this theta that is formed, this delta that is there, this delta is the deflection, deformation, and this theta is there, right? So delta is ml square upon 2 EI and this theta is ml upon EI. Similarly, if you apply a point load at the free end, your theta B is WL square upon 2 EI and your deflection is WL cube upon 3 EI. If you apply a UDL, then this deflection is WL raised to power 4 upon 8 EI, right? So these are some of the standard results. For a simply supported beam, if you apply a point load at the midspan, this delta at the midspan can be calculated as WL cube upon 48 EI. For a UDL applied over the simply supported beam, again this delta at the midspan, is 5 WL raised to power 4 upon 384 EI. Next is, for a beam having fixed support at both the ends, if you have a beam which have a fixed support at both the ends, then this delta which is there, this delta that is the central point load, due to the central point load, this comes out to be WL cube upon 192 EI. And last one is, for a fixed beam having an UDL, this deflection can be calculated as WL raised to power 4 upon 384 EI. You can just keep a check on all these standard results and you can remember them directly to be applied in the examination. Okay. Now the next point of discussion is the analysis of arches. When I talk about arches from gate point of view, analysis of 3-hinged arch will be one of the favorite topics from where the questions can be framed, right? When we talk about the analysis of 3-hinge arch, as you can see here, we have one hinge at point C. And due to the presence of this hinge, we have one additional equation in order to analyze this arch, right? For this arch, we have 4 unknown forces like this. We have 4 unknown forces. And when we take the equilibrium equations, we have only 3 equilibrium equations. Along with this 3 equilibrium equation, due to this hinge at the top, due to this hinge at the crown, we have one more equilibrium equations. Now using these 4 equilibrium equations, it is easy to have these 4 unknown reactions, right? So when I just take a section of this, arch like this, due to this general loading, the section of this arch will look like this. This is my point D. So this is my point D. Here the point D is here. So let me take a section like this, section XX. This is my section XX, right? So at point D, there will be one horizontal force and vertical force acting, and these horizontal and vertical force are due to the radial shear force. This is your radial shear force denoted by SD, and this is your normal thrust. This is your normal thrust, and this is denoted by your ND. This radial shear force is towards the center and this normal thrust is in the line with the arch, right? Now how to calculate this radial shear and the normal thrust? We have the direct relation that your radial shear is equals to HA sin theta minus RAY cos theta. Your HA is the horizontal force at A and RAY is the vertical force at A, right? Substituting these values, you can get the value of radial shear. Then for calculating the normal thrust, your ND is equals to HA cos theta plus RA sin theta, right? So using these two relations, you can calculate the value of radial shear and normal force over your 3-hinge arch, right? Next is, for a 3-hinge parabolic arch like this, if H is the height of the crown, right? This H is the height of the crown, then for any distance x, this y can be calculated using a simple relation. Y is equals to 4hx by L square into L minus x, right? So using this simple relation, you can get the value of y and you can also calculate the value of slope. So slope tan theta is equals to dy by dx is equals to 4h by L square into L minus 2x. Here theta is tan inverse of the slope. So for parabolic arch, you can calculate different values of y using this relation, and this is one of the important relation when we talk about the 3-hinge parabolic arch, right. So, this is all about the structural analysis up till this point. Moving on to the last point, if you need to draw the influence line diagram, right. So, Muller-Breslau principle is there for drawing the influence line diagram, right. So, if you need to draw the influence line diagram for the reactions, right, for the reactions, if you need to draw the influence line diagram, I'll just give you a quick example. For example, this is a simply supported beam, and for this simply supported beam, you need to draw the influence line diagram, right. For this reaction R, you need to draw the influence line diagram. So, now what you will do is, for drawing the influence line diagram, just displace this beam by 1 unit, displace this beam by 1 unit, right, displace this beam by 1 unit and draw the deflected shape of the beam. So, this is your ILD for reaction at point this. This is your ILD for R. This is your ILD for R. This is your ILD for R. What I said? If you need to draw the ILD for any reaction, then just remove that reaction and displace the beam in the direction of reaction by 1 unit. Then the deflected shape of your beam will going to give you the ILD for that particular reaction, right. So, this is how you can calculate, this is how you can just calculate the ILD, or you can have the ILD for the reaction at any point. Next, if you need to have the ILD for any moment, for any shear force, if you need to have ILD for any shear force, if you need to have the ILD for any shear force, have a, for example, this is the structure available to you. This is the structure available to you, right. If you need to have the value of ILD for shear force at C, you need to have ILD for shear force at C. Let me write this, shear force at C. You need to have this ILD for shear force at C. So, what you have to do is just shear this beam, just cut this beam from C, just cut this beam from C in such a way, just cut this beam from C in such a way that this total cut measure is 1 unit. This total cut is again 1 unit. This total cut is 1 unit. So, this will going to give you the value of ILD for the shear force at point C. So, this is ILD for shear force at C. This is your ILD for shear force at C. So, this is how you can calculate the ILD for shear force at C. Last one is, if you need to have the ILD for the bending moment, if you need to have the ILD for bending moment, if you need to have the ILD for bending moment, right. So, what you need to do is, you need to give the unit rotation at that particular point. You need to give the unit rotation at that particular point. For suppose this is your beam, and at any point C, you need to draw the ILD for bending moment, at C. So, what you have to do is, you have to just imagine an internal hinge at this point and give a unit rotation at C like this. Give a unit rotation at C. So, this is my theta 2 and this is my theta 1, right, and this is again my theta 1. So, what I will said that give the unit rotation at C, right. So, this is theta 2 plus theta 1 is again 1 unit. So, the deflected shape of the beam will going to give me the ILD for bending moment that is acting over the structure, right? So for any section, if you need to draw the ILD for bending moment, just assume the internal hinge and take and give this beam a total unit rotation. That is how you can have the ILD for bending moment. So hopefully all the important concept of structural analysis we have revised in the short span, and I guess whatever questions you face for structural analysis in GATE examination, you have all the listed formulas in this session. While using these formulas, you can easily solve all those questions. So this is all from my side with respect to the quick revision session of the structural analysis. You've been a great audience. Thank you so much for listening patiently, and I wish you all the best for upcoming GATE examination of 2023. Thank you so much.